All right. Thank you for coming to my presentation today. I'm Tony Brock Fisher, and I'm going to do a talk on tools and techniques for tracking down RFI. It used to be titled Tools, Tips, and Techniques for Tracking Down RFI. Well, that was too many T's, so I changed the title. First, a little background about myself. I've been a licensed ham since 1967 when I was 14. I had a 35-year career as a double E in biomedical ultrasound with HP, Agilent, and Philips. Retired in 2013. I've lived in my current QTH in Andover for over 30 years. I have two towers, a 78-foot and a 50-foot house bracket. I operate almost entirely HF, focusing on contesting, DXing, weak signal stuff on HF. And I live within about 1/8 of a mile of a 110 kV substation, and I actually have the 110 kV distribution lines going over an easement on the corner of my property. So what I'm going to talk about today is what is RFI. I'll give you a definition, what to do when you have a problem, getting your own house in order, trying to correlate and localize the source of RFI, some of the tools you can use to do that, and some of the things you can do to resolve the problem. So first of all, what is RFI? I'll give you a definition, and we'll talk about sources and paths and remediation. So I define RFI as RF currents from a source propagate via a path to a susceptible device, causing an undesired response. So sources can be switching power supplies, arcing power lines, digital circuitry, and even ham transmitters. And paths can be either radiated in the form of radio waves, as we all understand radio waves, or conducted. They can travel over power lines or over the power distribution circuitry in your house. And susceptible devices can be radios, TVs, hi-fi systems, arc fault circuit breakers, all kinds of stuff can be susceptible. So basically, the way that we can remediate RFI, there's kind of three opportunities to solve the problem. We can eliminate or reduce it at the source. We can modify the design or construction of equipment to add filtering, or we can change the frequencies that equipment operates on to move the frequency of the offending signal, or we can add effective shielding to the source. We can eliminate or reduce the path, which is basically adding shielding, and in this case we could add the shielding at the source or at the susceptible device or anywhere between. And we can add filtering to any conductors that come out of the source. And then we can also filter at the susceptible device. And now this would apply if, for example, your ham transmitter was causing a problem with some other device in your house, like an arc fault circuit breaker or other electronic appliance like a stereo system. But if the interference is actually getting into your ham radio, there's not much you can do in terms of filtering at that point, because that means that the signal is happening on the ham band frequencies. And so any filter you apply to your radio will also filter out the ham frequencies that you're trying to listen to. So this usually means that you're limited to the other two approaches for remediation. So you have a problem. You sit down to the rig, and instead of hearing your fellow hams, you hear zzz or some other kind of awful noise on the radio. So the first thing you want to do is try to identify the source by its sound. If the source has the characteristic 60 hertz buzzing, then there's a pretty good likelihood that it's being caused by some arcing or something in some appliance or in the power lines or outside, on your street, on a power pole. Does it repeat across the band? And by that I mean, do you hear a similar noise every evenly spaced distance across the band? Like maybe every 18 kilohertz you hear the same kind of buzzing tone. That would tend to indicate that it's probably a switching power supply, and we'll talk about why that would be. Does it have a 60 hertz component? So you can figure out if it has 60 hertz if you have a scope. Almost any oscilloscope has a line sync trigger on it. And so you can run the audio from your radio into a scope and set your scope up to do line sync triggering. And then if the noise is stable, if it stays in one position on the screen, that tells you it's 60 hertz synchronous. And that's a good tip that it's probably being generated by something that's hooked up to the power lines, or maybe it's the power lines themselves. Does it come and go, or is it always there? Does it come at night, or does it disappear at night? Is it there 24/7? Is it there only during working hours? I live close to an industrial park, and I used to have a noise on 160, and fortunately for me, it was only there during working hours. From 9 to 5, there'd be this nasty noise on 160, but I operate 160 at night on the weekends, and so that worked out okay for me. Is it weather dependent? If it only comes when it rains, or if it only comes when it's dry and windy like today, that can be a hint that it's some kind of an event happening in the power pole, in the telephone pole power distribution systems. Sometimes the insulators get a crack in them, in which case, when the water gets in the crack, that can cause a problem. Other times, there can be a loose connection, in which case the water actually helps the connection and quenches the arc. But then when it dries out and the wind blows, it can make that connection come and go and make it let it make noise. So the first thing you want to do is get your own house in order. And basically the way you do this is to arrange to be able to listen to the RFI with some kind of a battery-powered radio. Whether you can run your station transceiver off of a car battery, a lot of people have it set up that way anyway for emergency backup kind of thing, or if you have another kind of a radio that's battery powered, set that up to listen to the RFI and then kill the main breaker in your house. And of course, nowadays, your house probably has 3 or 4 people using a computer on it, so you want to make sure you let them know that you're going to kill the power before you just go and kill the power. And you might also want to make sure that you're not taping the last episode of some show that you're interested in watching. So anyway, you kill the main breaker in the house, and if the noise keeps going, then you know it's not coming from anything in your house. And at that point, it's time to go on a noise hunt. If the noise stops, then what you do is you turn the branch circuit breakers on one at a time and localize the source until you hear, we turn on a breaker, you hear the noise come back, then you know it's in that room or on that circuit. So by far the biggest problem that I've run into in tracking down RFI sources outside of the house is to correlate and localize. And basically the main receiver that you use at your ham station, the HF transceiver, is extremely sensitive, and you usually have it connected to the station antenna, which is usually optimized to work pretty good. Even if it's just a dipole, it's going to give you excellent sensitivity. Or if you have a rotary beam, that's going to give you a lot of signal into a very sensitive receiver. So what this means is that fairly small signal levels of RFI are going to be annoying. I mean, they could be S7 and be annoying if you're trying to have a QSO. Now, what you're going to do when you go on a noise hunt is you're going to use a portable receiver and a much less sensitive antenna, and that's going to give a much smaller signal level to work with. And so the trick is trying to make sure that what you're hearing on the receiver you're carrying around with you is in fact, it's the same noise source as the one that's bothering you when you're sitting in your ham shack. So if you have a rotary beam antenna, that's a good place to start. You can swing that through 360 degrees and figure out where the noise is coming from. And most antennas have a main peak response in the direction they're pointed, and that's fairly broad, so that may not give you a really accurate indication of the direction that the noise is coming from. But most beams do have some fairly sharp nulls off the back. And if you can figure out where that null is, you can use that as a way of more precisely figuring out the direction that the noise is coming from. And if you have some other hams in town that you're friends with, they can probably do the same thing. And if you're fortunate, they'll be able to pick up the noise source and give you a direction, and you may be able to triangulate between the two of you and kind of hone in on it. So as I said, it's not uncommon for the RFI to be completely undetectable on a small portable transistor receiver and a portable antenna. And so what you may have to do in that case is try to locate the signal by strength instead of by direction, and basically walk around or drive around the neighborhood and hope to get lucky that you get near the noise source, in which case it'll get much stronger and you'll be able to locate it that way. So I'll talk about some of the tools that I use to track down noise. Probably the gold standard is the Sony ICF 2010. It's a battery-powered shortwave radio. It covers from low frequency all the way up to VHF. It has an internal ferrite antenna. It has a whip antenna, and it also has an external antenna jack. And one of the good things about it is that it has an AM detector on the VHF aircraft band. So the aircraft communicate up around 130 megahertz, and they use AM. And the reason they use AM is so that if two airplanes are transmitting at the same time, you can actually hear them both, as opposed to FM that would have a capture effect and where one of the airplanes wouldn't get heard. And so for safety, that's why they use AM. And we'll see later that this had the advantage that you can use a small Yagi like this one here to actually locate and get some direction bearings on an arc or some kind of an RFI signal. So if you hear a signal on your radio, say on 20 meters, if you can correlate it with a signal that you can hear on this radio on 135 megahertz, then you're in luck. You can use the little antenna to triangulate on it and track it down. Another thing you can use is any kind of a QRP rig. So I've shown a KX3 here, but you could also use a IC705 or FT817 or any other, HF rig or VHF rig that is designed to be portable. So the thing is, you're going to probably have to do some driving around or walking around in order to localize the noise source. This has the advantage that it's very sensitive in the HF band. So at least you have a chance of correlating what you hear with this to what you hear on the hams on your own transceiver in the ham shack. So you could start by hooking up your beam to this in the ham shack and say, yep, I hear it. I know what it is. And then hook up another antenna and see if you still hear it. Then you say, yep, okay, still hearing it on the KX3. Now you're ready to walk out of the shack and start walking around the neighborhood. So I'll talk about some of the antennas that I've used for hunting, and this is nothing special to me. This is the kind of conventional knowledge or conventional wisdom. One of them is a shielded magnetic loop antenna. And basically, it's a small, portable, directive antenna that works at low HF frequencies, and it has a very sharp null to locate sources. So basically, this antenna here would have a very sharp null in the direction that I'm pointing. So if the signal is coming from over there, if I aim it like that, you can hear the signal pretty well, but then as you turn it this way, you'll hear a null. And it doesn't matter whether it's this way or that way. You're going to get a sharp null off of both directions. And so in this case, what you're doing is you're trying to pick up the signal with a null. And so this is just a piece of coax, and you can't tell, but underneath all this electrical tape here, I've cut the shield. And so it's actually shielded all around, but the shield is broken in one spot, which allows the center conductor to act as a shielded magnetic loop. And then inside the box is a tuning capacitor that is used to make the antenna work well at HF frequencies. So another antenna is the known as the W1HIS handheld magnetic loop. W1HIS is Chuck Conselman, who has done just a tremendous job of detailing how to use ferrite cores to suppress noise in your house. If any of you have ever been to Chuck's home, you know that it's basically a shrine to ferrite. He has ferrite on everything. But he's developed this little magnetic loop antenna that works with the Sony radio. Basically, it's a piece of shirt cardboard or cardboard off the back of a pad of paper in this size, basically 2.5 by 8.5 inches. A small diameter RG174 coax runs around the edges of it. You tape it to it, and you solder the center of the coax to the shield at this point, and you leave the shield at the end here open. And this also forms a shielded magnetic loop. And this also has a sharp null in the direction of the loop. And you can use this, you can walk around your house, hold it up next to power lines, hold it up next to appliances or anything, and it's very effective at localizing noise sources in the house. And then there's also the 130 megahertz Yagi antenna, and I've got one here. You can see it's nothing fancy. I built this one, I don't know, 20 years ago when I was having a lot of RFI problems. And it's just, you know, aluminum elements stuck through a stick of wood, and it has a little gamma match, a little choke on the feed line, and the feed line goes to this box here. And I could connect this to the Sony radio. And the good thing about the Sony radio, as I said, is it has an external antenna jack. And when you plug an antenna into it, it disconnects the whip antenna and the ferrite inside. Because you don't want to be picking up on more than one antenna. You only want to be picking up on the antenna you're using to hunt the noise. Otherwise, you're going to get confused. So what I have here is inside this box, I have a Radio Shack transistor radio that you used to be able to buy when Radio Shack was still around. And it has the aircraft band on it. So this radio is set up on 135 megahertz, and it's in a shielded box because with this case, I had to find a way to connect the antenna to the radio, and I wasn't able to disconnect the ferrite antenna. So I put it inside the shielded box, and that way it's only listening to what's coming from the Yagi antenna. So, you know, once you have this set up, it's real simple to just walk around and kind of point the antenna at this phone pole or that phone pole and see which one you hear. So one other tool that I didn't describe in the talk, and I didn't bring one with me, is actually it's an acoustic device. It's a parabolic microphone, and you can point this at a power pole, and you can actually hear the arcing acoustically, and it's very directive. So with that kind of a device, you could probably get it down to which insulator it is at the top of the pole. They used to sell a thing like that as a toy, and the one I have is the toy version. But the power company, if you get as far as getting them out to find your problem, they'll have one that's very sophisticated. It's actually built for the purpose, and it's not listening to sound that we can hear. It's listening to ultrasound. It's listening to like 40, 50 kilohertz. And that way it's even more directive, and it cuts out some of the other natural sounds around. So next we're going to move on and talk about resolutions. What are some of the things you can do once you've found the source? And a lot of the resolutions are going to be concentrated on switching power supplies. So basically nowadays, switching power supplies have proliferated, and they really are the bane of amateur radio operators. They're awful. You know, there's one right there, and you know, there's probably 3 or 4 or maybe 8 over there, and there's one right there. And so I didn't have to worry about bringing one as an example, because they're all over the place. Cell phone wall warts. In the old days, if you had a wall wart, it had a little bit of heft to it, and that's because it had an actual transformer in it and was a nice linear supply. Nowadays, they don't weigh nearly as much because they're built with switchers. So in a switcher, a DC power source is turned on and off by a saturated switch, and that means that the switch is either completely on or it's completely off. And that means that there's very little energy dissipated in the switch. So if the switch is on, there's lots of current flowing, but the voltage across the switch is very low. If it's off, there's lots of voltage across the switch, but there's no current flowing through it. So there is never both, and we know that power is voltage times current. So by not ever having current and voltage at the same time, they can avoid dissipating power in the switch. And that is why switchers are very efficient. So the voltage that they chop with this switch is converted by a transformer or an inductor to the desired output voltage. And higher switching frequencies mean that any transformers or inductors that they have to put in there to do this conversion can be very small. If it was 60 hertz, the transformers would have to be this big, but because it's running at 100 kilohertz, it's just like a little ferrite core. And then the output is rectified for DC or filtered, and as I say, they're cheap, efficient, but they're deadly for ham radio, and they're just all over the place, and they're propagating like rats. So if we look at this chopped frequency, basically the switcher is producing a square wave. And so a square wave has many harmonics. It basically consists of a fundamental frequency and all the odd harmonics. And so we can see that if we had a switcher that was chopping at 1 kilohertz here, it would have 3rd, 5th, 7th, 9, 11, 13, 15, 17, 19, 21st harmonic would be at 21 kilohertz here. And you can see that the first couple drop off quite a bit, but then it kind of levels off. So when you get up to the 21st harmonic, it's only down about 28 dB from the fundamental. And those harmonics can continue on up much higher and get into frequencies where you're concerned about in the ham bands. So how do you control the RFI that comes out of a switcher? So a switcher can be considered as a 4-terminal device with 2 input connections and 2 output connections. And those 2 sets of conditions might share a common ground. The RF is generated internally, and it can be conducted out of the device through either side, either the input side or the output side. Reasonable engineering practice includes putting a capacitor across the input and output terminals. And there's also some small amount of capacitance between the internal ground, which may be floating, and any external ground. And so therefore, what comes out of switchers is primarily common mode on the input or the output connectors. And I'll tell you a little bit more about what common mode is. So here's a kind of a very coarse diagram of a switcher. You have power coming in here. You have some kind of a switching device which is either completely on or completely off, driving a transformer, and then the other side of the transformer, we just rectify it, and maybe have a filter capacitor here, and here comes the output of it. So if this was a wall wart for a telephone charger, you know, this would plug into the wall, 120 volts AC, and then this side over here would be your 5-volt USB voltage out. And this whole thing could float, and even if it floats, there's still going to be some capacitance from the internal ground and a real ground. So basically switchers, because of the way they're generated, they work, they have these capacitors here, which basically say that as far as RF is concerned, these 2 conductors are the same. Any RF that's coming out is going to be coming out on both conductors. And that's what we call common mode. So common mode means that the RF current is going in the same direction on both conductors. If it's a power cord or an antenna for stereo or something else, the RF is traveling in the same direction on the 2 conductors. And then the other mode is differential mode, and in this case, the RF current is traveling in opposite directions on the two conductors. And this is basically what happens on ladder line, on your feed line, or inside your coax, is you have RF current flowing, for example, on one side in the center of the coax, and in the other direction on the inside of the shield of the coax. And whether it's common mode or differential mode, we have to do different things in order to be able to prevent it from coming out of the switcher. So in common mode, we would like to introduce an impedance in all of the conductors of the cable. And we can do that by adding a ferrite bead around the cable. And that does not eliminate differential mode. If it is differential mode, then we have to introduce an impedance in each of the conductors separately and possibly have a bypass path to ground in each of the conductors. So in that case, we basically need to add a filter. And you may need to do both. And I'll give you some examples of where that happens. So here's a common mode choke. This is one that I built for my solar system that was part of the article that I wrote in April 2016 QST. And so basically common mode introduces an impedance in all the conductors of a cable by adding a ferrite bead over the cable. It does not eliminate differential mode noise. So if you think about it, this is all about magnets. And if you wind wire around a magnetic material and put a current through it, you'll get a magnetic field. But if the current is flowing in the opposite directions in two wires going through a core, those magnetic fields are going to cancel. And the core won't know that there's anything going on. It won't experience any magnetic field, and therefore the wires won't know that there's a core around them. So that's why cores don't do you any good for differential noise. A lot of hams get to the point where they start to understand that they can solve some RFI problems by throwing a ferrite bead on something, and that works in 90% of the cases, but in the cases where it's differential mode, that won't do a thing. So what's important if you're going to try to fix RFI with a common mode choke is choosing the right core material based on what frequency you're worried about and the arrangement of the conductors on that core. So if you go to choose a magnetic material, here you'll be able to go on the web and, for example, if we were using material made by the Ferrite company, we could put in a part number and we could, on the web, we could get a plot like this of the impedance of that core. And this plot is shown for one turn through that core. If we put two turns through that core, we know that the inductance goes as the square of the number of turns. And so we would get a lot more inductance, a lot more inductive reactance if we put more turns on the core. And sometimes in the data sheets on the web, they'll show you curves for 1 turn, 2 turns, 3 turns, and so forth like that. Basically what we're looking for is we're looking for a high impedance at the frequency that we're concerned with. And basically, you'll see that a core has an inductive part, which is the reactance, and a resistive part, which is basically dissipating energy. And what we want is a high impedance at the frequency of interest. So this material here is material 75, and that's told by the third and fourth numbers of the part number. And so this is mix 75, which is a particular set of ingredients in the ferrite that they use to make the core. And this one's particularly effective at about 1.8 megahertz. So guess what? That would be awesome if you had problems on 160. Okay, that would be the one you'd want. And then this one here is mix 31, and this one is good for anything from 1 megahertz to 300 megahertz, but it peaks up pretty high up here at about 200 megahertz. But this is a good one for general HF use. And then there are a lot of other mixes available. These are all Ferrite company numbers. Other manufacturers would have different numbering schemes. But in general, for low frequency, 1 to 5 megahertz, 160 or 80 meters, you'd want mix 75 or mix 77. 77 is an older and cheaper material. 75 is brand new and quite a bit more expensive. For general HF, 1 to 30 megahertz, you'd want mix 31, which is the one I prefer, or mix 43, which is a little bit higher in frequency, but it's still good for HF. And then for VHF, 30 megahertz and up, I would suggest mix 61. And so these are some pictures of some ferrite cores. This is a 2.4-inch diameter bead. This is about a 1-inch diameter with about a 1/2-inch diameter hole. And this is one of the snap-on types of cores. So the snap-on cores are very convenient because you can just take them and put them onto a cord without having to worry about fishing the cord through the core or whether a plug on the end would fit. However, a solid core is always better than a snap-on core. When you snap these two together, even though the surfaces, the mating surfaces are polished so that they'll mate very closely, there's still a slight air gap in there, and that reduces the amount of magnetic field coupling that you can get in this core. And so for the same size core, a solid core is always better than a snap-on core. And if you do use a snap-on core, do not rely on the plastic shell to hold it together. I mean, it might hold it together for 5 minutes while you test it, but if you decide that it's doing the job that you want, always put a cable tie around it so that it holds it together, because over time, that plastic shell will creep and the halves of the core will come apart, and then there'll be an even bigger air gap in it, and it'll completely lose all of its efficiency. So we'll talk about common mode choke and the arrangement of conductors. And the cardinal rule is all the conductors must pass through the core the same number of turns in the same direction. And I get a lot of people, I probably get 1 or 2 emails a month now still from that April 2016 article about solar power. And the thing about that is that a ham will call, he says he's got a solar system or he's got a neighbor with a solar system that's creating a big mess on his radio. What does he do? And I tell him, well, you got to go up there and put these ferrites on. And the thing is, he's not going to go up there. You know, he's not going to be part of that job. He's going to hire somebody to do that. And the people he hires are going to look at these donuts, that's what they're going to call them. They're going to say, oh, there's some nice looking gray donuts, and they're going to wind some wires around it and think they've done a good job. Well, they won't do a good job unless they follow this rule. And so I always reply and I say, the cardinal rule, all the conductors must go through the core for the same number of turns in the same direction. If they're going in opposite directions, then that common mode current is going to cancel just as if it was differential mode and the core's not even there. If there's an extra turn on one than there is on the other, you might have enough choking impedance on the one that has the extra turn, but not enough on the one that missed a turn. So that's the cardinal rule. Another thing to remember is that the inductance increases with the square of the number of turns. So 2 turns on one core is twice as good as 1 turn on 2 cores. Or 2 turns on 1 core is 4 times better than 1 turn on 1 core. So you always want to try to get multiple turns on it. And so this is another reason why you might want to use one of the bigger cores that has a nice big hole. You could probably get 8 turns of RG58 on this core, but you'd probably be lucky to get 2 on this one. So that's why the larger cores are sometimes better. And so trying to get more turns on it is useful and it's often better, but there is a point of diminishing return. So there is capacitance between the turns, and if you get too many turns on there, you'll end up having so much capacitive coupling through it that you're defeating the purpose of having the inductance part of it. And that kind of gets beyond kind of the intro level. So in order to really know if a core is working properly, you have to measure it, and that's fairly sophisticated measurement to make. So, you know, you can try a few more turns if you get more turns on. If it helps, great, but don't always just put like the max you can do. So now we're going to talk about differential mode noise and how you would deal with that. So in this case, you can't fix the problem just by throwing a core on the cable. So basically, you need to come up with a filter that filters out the differential signals that flow in opposite directions and don't create net magnetic fields. So we do this with basically inductors and capacitors. So here's an example of the circuit of a differential mode filter, and you can see that it has an actual low-pass filter in this conductor here, and it has actual low-pass filters here and here. These are also coupled inductors, and so these also are effective for common mode as well. So this one would do both common mode and differential mode. And differential mode line filters look like this. This is a typical core-com filter that you could buy and put it inside a piece of equipment, or maybe you open up a piece of equipment and hopefully you'll see that there's one there. This is a higher power filter. This is for probably 50 or 60 amps for three-phase power, and you can buy these for three-phase or 240 or 120 volts, and so you can run power through these to something that might be generating RFI, and that will prevent the RFI from continuing to travel on the power grid. So now I'll talk about some specific techniques. As I said, I did a lot of work on remediation on the solar panel system that I installed. The way it works is that all of the panels generate about 400 volt DC on the roof, and this comes down to a central inverter, which is a big box, and that is basically another big switcher, and that converts the 400 volt DC into 240 volt AC at about 60 amps, and that puts that on the grid. It's a direct connection to the power grid. And so on the connection to the power grid, I did both a differential filter, which is this thing here, and I had to make sure it was all done according to code. It had to be an electrician that did the work, so it had to be in its own metal box. But this is a differential mode filter, and then over here is the common mode filter that has like 30 really large ferrite chokes in each of these pieces of PVC pipe. So it's basically one turn through about 60 chokes. And those two are very effective at killing anything that's coming out of the inverter from getting onto the power lines. And we'll talk a little bit about resolutions and FCC regulations. So one point of confusion is that the FCC regulations say that the operator of a device for Part 15 is responsible for fixing any RFI issues with it. And so, well, who is that? Is that, the homemaker, in the kitchen with the refrigerator? Who has the technical savvy? And the funniest thing is that the FCC statement says, if you have any problems, just refer to an experienced radio TV technician. Have you met an experienced radio TV technician lately? Do you know any radio repair shops? No, they don't exist anymore. It's a myth, but still the FCC talks about it. So one issue is, who's responsible, and why are we having a problem anyway? So here are a couple things to know about Part 15. So components are tested by the manufacturer, supposedly, and they're labeled that they meet FCC Class B. And there's no guarantee that they meet that spec once they're in a different configuration. So they test it somehow in a lab to see if there's noise coming out of it. But then when you take it home and you plug it in, if you run the cord across the room or run it near the TV, all bets are off. The testing that they do under 30 megahertz or the HF ham spectrum is not that strict. They're more strict at VHF. And the really tricky part for solar systems is that it only applies to line-connected devices. So in a typical solar system, they have panels on the roof, Each panel has a switcher under it, and its job is to convert the panel voltage, which is 35 or 40 volts, up to that 400 volts that you're going to get off the roof. And those aren't connected to the line, so they're exempt from Part 15. So here's the FCC Compliance Statement. I love this. Consult the dealer or an experienced radio TV technician for help. Now, if you took your phone charger into Best Buy, who is the dealer, and said this is causing RFI, they would give you a blank stare. And again, the operator of the device is responsible for correcting it. Now, in a solar system, there are many forms of ownership, okay? I bought mine outright. I could have leased it. I could have, entered into some kind of an agreement with the power company. And under those different scenarios, there are different operators. I own it, I'm the operator. But if I leased it, then the person I leased it from is the operator. So there's all kinds of chances for finger pointing and evading responsibility. And then the question is, who has the technical savvy to fix it? I already identified that the manufacturers don't know what they're doing, the installers don't know what they're doing. So most of the time it's up to you. You're the guy with the most smarts, or the gal with the most smarts, to go in and fix the problem. And so you're going to have to learn to play well with others, get along with your neighbor, try to get access to whatever it is that's causing a problem, and try to apply your knowledge to fix the problem. So I have a few war stories that I'll briefly tell. One of my favorite ones is when I retired in 2013, we redid the kitchen and we got all new appliances. And one night I'm listening to the radio after I had just done the dishes, and I hear this strange noise on my radio. And I kid you not, it sounds like dripping water. I'm saying, why am I hearing dripping water on my radio? Long story short, it was RFI coming from the dishwasher. So almost all new energy efficient appliances achieve energy efficiency by having variable speed motors, which means they have a switcher in them. And the switcher is how they control the speed of the motor. And so in this dishwasher case, I first tried winding the power line around a core. That didn't really help. What I ended up having to do was to buy a line filter for it, which I got off of Amazon, and added the core, and that solved the dishwasher problem. I still got a few minutes. We bought an electric scooter up here at Horse Traders, and it came with a charger. And what's that? Time? You're going to kick me out? So I was delayed 5 minutes by the guy before me. So, it's true. No, I'm supposed to yell at you, right? All right. Probably the one on this list that is the most interesting and informative is one night I'm on the radio, turn on the radio, I hear this horrendous 30/9 arcing, 60 hertz power line noise. I say, what the hell is that? So it's dark, I go flying down my driveway, looking up and down the street, and 2 poles down the street, the pole is on fire. I mean, the arcing was so bad it had started a fire. And I called up the power company and I said, your pole is on fire. And they showed up very quickly, much quicker than when I call them and say, I'm getting RFI from your pole. So there's a tip there in there somewhere. I won't tell you what it is, but they showed up very quickly when the pole was on fire. So with that, I'll take one question. Then after that, I'm supposed to take questions aside. Go ahead.
Question on Zoom.
I discovered by pointing my antenna to the house across the street, recessed lighting has a thermal switch. Thermal switch was arcing to the point I could hear it. I walked into the house with my little portable radio. I could hear it electrically. But then I could fly to the kitchen now and turn the lights on. You could hear it audibly. The homeowner never knew what that was. He couldn't figure it out. And luckily, we stopped having fire.
Yep. Yep.
Is it to be posted somewhere?
I think it's going to be on YouTube, right? You guys post these videos online? All right. Thank you very much.
Question on Zoom.